Hello, welcome back to Engineering 211 Statics, and I wanted to continue on from last time. We talked about equilibrium. We finished up a 3D equilibrium problem, and now I wanted to talk about structures. If you're following along in your textbook, we're looking at Chapter 6. We're going to first start with trusses, and then we'll get into frames and machines as we look at this interesting chapter. And as I talked about last time, a lot of what we're doing in here is really just the application of what we've learned in the past, that being equilibrium. So when we go to study trusses, I might draw some trusses here, and whether we're probably not going to be too concerned whether you know the names of all the trusses and things like that, whether you might have a truss like this that you would use to support. Maybe it would be a rail truss or a highway truss or something like that, or maybe you have something that looks like this that you use to support roof loads. Okay. All kinds of different possibilities for loads there. So you can do some research and see what they mean by a Pratt truss or a Warren or a Fink or something like that. But our purpose is going to be to look at these trusses and try and analyze them. Most of our trusses initially are going to be a two-dimensional truss. They'll be in the plane of the paper. A lot of times, and even these ones I've described often comes in pairs or multiples, and then you'll just keep repeating that. We will, before we're done, get into a three-dimensional truss, a space truss, which is kind of interesting. But initially, as we talk about it, we'll talk about these plane trusses. So some of the assumptions that we need to make on the, well, maybe before I get into the assumptions, let me talk a little bit about how the truss is made up of triangles, right? So the basic element is a triangle. So you could imagine if you have something like this, maybe we have it pinned here, and we have a roller here, and we apply a force like that, or we apply a force like that. That's going to remain rigid and actually work out. Let's say that we do something like this, and I apply a load like this and a load like that. And if these are pins, we'll talk more about that. I think you could imagine that if you applied this load very quickly, this thing would change shape, wouldn't it? So that's not going to work out that well. Now you could take this and correct it if you wanted to. Put the brace on it. Anyone that's maybe braced up a sagging gate or screen door or something like that recognizes that if you put a brace across there, and you apply these forces, things are going to be okay again. That's because you've gone back to the basic element of the triangle. And there's actually an accounting for this. If we talk about J being defined as the number of joints or pins, okay, where these are put together. So I have a pin there, and I have a pin there, and I have a pin there. So the number of joints or pins. And if I talk about M defined as the number of two-force members, so all of these are two-force members. That's the requirement for a truss. It has to be made up of nothing but two-force members. So I have 3 two-force members there, I have 4 two-force members there, and so on. With these two numbers, we can talk about the relationship of M plus 3, and if that's equal to 2 times J. If this equality is true, it's okay. It's a good truss. It's stable, and you can work it out. What happens if you have M plus 3 greater than 2J is it is redundant, it has redundant members, and we will say that it is statically indeterminate. Okay, you're probably not going to be able to analyze it. And then the last possibility here is if m plus 3 is less than 2j, it is unstable. Okay. So let's look at this one. We would have what? The number of joints, j, is equal to 3. The number of members, m, is equal to 3. And I get 3 plus 3 is indeed equal to 2 times 3. So as we thought, we can analyze that one and it's okay. This one here, I have j is equal to 4. The number of members then is equal to 4, because I have 1, 2, 3, 4 joints and 1, 2, 3, 4 members. So then if I look at this equation, 4 plus 3, and how it's related to 2 times 4, so I have 7, which is less than, what do we have on this right-hand side? 2 times 4. So we have this, it's unstable. And if I look at this one, what do we have? We've got the number of joints is, again, 1, 2, 3, 4. Okay, they're all pinned. Number of members, 1, 2, 3, 4, and then this fifth, the diagonal brace across this, so m is equal to 5. So when I look at m plus 3, 5 plus 3, is that equal to 2 times j or 2 times 4? It is indeed. So that's okay. Now, sometimes people say, well, if a little is good, a lot's better, so why don't we try something like this. We put a brace in here, and we put a brace in here, and I'm just going to say those braces go past each other, that they don't touch in the middle. We could constrain it there, and then we'll apply the loads like that. What do we have here? Well, j is still equal to 4. M now has gone to 6, so I have 9 is related to what? 2 times j is 8, or 9 is greater than 8, so I'm back here with this one. Statically indeterminate, right? Okay, I couldn't really analyze it because it's over-constrained. This one was enough. When we added one more, it's over-constrained. Now, sometimes we'll take this, and you could imagine if you were to apply a load like this, that this one is probably going to be in compression, and this one would be in tension. So if these are thin cables or rods, we could then make the assumption that this really rather looks like this. How does a thin cable or a rod work in compression? Doesn't work well at all, does it? Okay, so you would have something that would look like that, and then you would have this one as the only functioning one, and we could model it right back like that. Okay, so depending on how the members are laid out, this may or may not be a problem. The reason I bring this up is we do this all the time in construction. Putting thin rods or cables there is a very efficient way to do this, because a lot of times we don't necessarily know which way the load's going to come from, particularly these lateral loads, whether a wind load or a earthquake load. It could be coming from one direction or another, so we could put the braces in there and have a very light, very efficient system. And we can still analyze that, because when it goes into compression, the thin brace is not going to do any good. But if these were both heavy, I mean, if these are both heavy I-beams or something like that that would hold a lot of compression, we would be stuck at that point. Interesting, they also use this in airplane construction. If you look at the way biplanes were constructed, they had a wing across there and a wing across there, and they would usually have some spars and crosses like that. So it was a lot like that, which is good depending on how the loading was. If you invert and whatnot, you can have very different loading on that airplane. So it's kind of interesting uses of trusses and very efficient uses of trusses. So I wanted to go through that analysis. Most of the trusses that we'll be doing will fit into this one or that one, although occasionally this will pop up and maybe we'll have to make some assumptions. But for now, most of them will be like this. Well, some assumptions that we're going to have to make so that we can analyze trusses. So some of the things we want to assume. The deformation in the members is negligible. So deformation in the members is negligible. That these pieces in this truss, if we have something like this, to look at a very simple truss, and maybe we'll analyze something like this before we're done today. But this member here, that member there, probably in compression, we're not going to figure that they change very much in their dimensions, that they don't get appreciably shorter. For our purposes in here, we're thinking of everything as a rigid body, so we want to look at this distance, that length, being a constant. Okay, so that's important. Some other assumptions. All members are two-force members. So if I take a section out of here and I look at what's going on with that, I either have compression in it or I have tension in it. Okay, so it's a two-force member. That's a requirement. If your truss has even one multi-force member that's more than a two-force member, it's no longer a truss. It'll be a framer machine. We'll talk about that later. Member weight is usually negligible. The member's weight is usually negligible, because if I've got a two-force member like this, let's say it's under compression, and then I look at its weight here, is it a two-force member? No, it is not. How do we handle this? Usually we can just say that the weight is really very small compared to the loads that it's going to be holding. If that's not acceptable, what you're going to do is you're going to apply that weight. You'll put some of it there and some of it there. So you'll move that weight and put some of it at each end, and then you can still analyze it pretty well, and it's still going to be a two-force member. That goes to this one, loads only at joints. Okay. We haven't talked about distributed loads yet, but let's say that you have something that looks like this, and maybe you have some snow load on there like that, or some dead load on it. What do we do with that? Well, we're going to have to again model it, where we take some of that load and put here, and some of that load and put there. So we only have the loads at the joints. That's important. You're only loading at joints. There's secondary moments that are involved when you do this, and you go to an advanced class and you'll talk about it. Usually they're not that big a deal, actually. The primary moments that we're going to be talking, or the primary forces, stresses that we're going to be talking about, are the biggest. And we're going to model all joints as a pin. Okay, so we're going to talk about taking a member and putting a hole in it, and then maybe another member and a corresponding hole in that member, and you put a pin through there. Okay, now not many trusses are like that. A lot of times you'll see a truss that's made like this, and they put a gang nail on there or something. You maybe have a gusset or a pressed on gang nail, those metal gang nails. Those are they press those on. I at one time thought those weren't very sturdy, and then I had to try and pull one off when we changed a truss out one time, and they stuck on pretty well. So from a fire standpoint, it's a bit of a problem. They don't hold up as well as other methods in a fire, but because actually metal weakens quite a bit when it's exposed to heat, whereas the wood just kind of chars, and that process takes a while. So this has some disadvantages based on other things, but you can still model it pretty well with a pin. Some of the sky bridges around campus, you might see members coming together like this, and it's welded together, you can probably still analyze that as a pin. If they start putting great big gussets in here and reinforcing it, then it's probably not going to model as a pin very well. But unless you start putting massive reinforcements in here, it's still going to probably analyze as a pin pretty well. So our first time through this, if you go into the structural business, you'll start to talk about more sophisticated analysis and doing away with some of these assumptions. But the first time through, and for a lot of trusses, you can really do pretty good work with this. Well, let's try a problem then. Well, I guess we should talk about how we're going to do this. So before we get into the problem, so we've got two methods. We're going to first talk about method of joints. Which is essentially a free body diagram of each pin. Okay, we're going to draw a free body diagram at each pin. So let's say that we have something like this. This is the end of the truss here, and maybe this has some tension in it. And then we have this piece like this that has some compression in it, and we had some reaction here. We've got a roller that this thing sits on. If I were to draw a free body diagram I'm going to draw a free body diagram of the pin using method of joints. This member is going to be in tension, right? This member is going to be in compression, and I probably need to deal with the reaction there. So I have the reaction look something like that. And we then go back to chapter 3 material. Essentially, we have some of the forces in the vertical direction is equal to 0, some of the forces in the horizontal direction is equal to 0. So we can really tolerate two unknowns with this problem, in a plane problem, in a two-dimensional problem. Now, this is the first one that we're going to do. The next one, and I'll just throw this out here, we'll spend more time talking about it. It's a method of sections. Which is you take a section, or you look at a free body diagram of a section. Well, what in the world does that mean? If you take a truss, maybe like that, and I slice through here, I'm going to look at a free body diagram of this thing. And maybe this top piece I would put in as a force, and this bottom piece I would put in as a force, and then I'd have something like that. And I would, of course, have these reactions over here, reaction 1 and reaction 2. So I'm going to slice right through here, and I'm going to take, I can't just cut through that, but I can cut through it and replace that member reaction with a force. So I'll be able to then hopefully find those. Okay, so that's what our task is. This will be the second one that we do. So we'll look first at method of joints, and then we'll go to method of sections. This is essentially equilibrium with chapter 3. This is essentially equilibrium with chapter 5 of your textbook. All comes back to drawing your free body diagrams and looking at equilibrium. Well, let's try one here. A lot of times you just need to climb up on the bicycle and see how it goes. So let's try a very simple truss. Let's say we have something like this. Maybe this is 10 feet here. We'll say this is 45 degrees. That's 45 degrees. Give me a right angle there, wouldn't it? And I'm going to apply the load here. I'll say that I just have a 1,000 pounds there, and we'll take a pin connection here at A. We'll call this B, and a roller connection here at C. And my task is, given this, I'd like to find the force in all all members. Okay, and this is going to include a magnitude and a direction. The direction being whether it's in tension or compression. We'll talk about how important that is in a little bit. So if we look at this, I mean, if you want to go back and you want to talk about the thing we did a couple slides ago, we're talking about the M's and the J's. We have J is equal to what? 3, and M is equal to 3. 1, 2, 3, A, B, C, 1, 2, 3. So we've got 3 plus 3 is equal to 2 times 3. Looking back on this thing, it looks like I made a mistake here. I have the 2 times 2. Let's see, that should be 2 times 3 because it's 2 times J, 2 times 3. There we go. And we're okay. Good. So back here, 2 times 3. So it's okay. We should be able to analyze this. So let's go ahead. I think what we're going to need to do is we're going to find our reactions first. So I can draw a free body diagram of this entire thing. And I'm going to have some force AY here, and I could say that I have AX. I could put this 1,000 pounds down like this, and I could have, this is a roller, so I will just have C like that. Now we know by the geometry here that would be at the center, so this would be 5 feet and this would be 5 feet. And if I sum the moment about A, setting that equal to 0, I have 1,000 times 5 minus C times 10. So C turns out to be equal to 500 pounds, doesn't it? Most of you, just by inspection, would probably recognize that. But if we were then to sum the forces in the vertical direction, setting that equal to 0, I have AY plus C minus 1,000. We make the substitution for C. And AY is also equal to 500 pounds. Okay, so we've got those. We could have said very quickly up here, some of the forces in the horizontal is equal to 0, which is equal to AX. So AX is equal to 0 with the load being vertical. That's true. So we've got those reactions. So I think what I'm going to do is I'm going to go ahead and I'm going to then do a free body diagram at pin A. So a free body diagram at A is going to look like what? Well, I have AX and AY. So I have 0 there, and I have 500 there. And then I've got this member. I've got force AB. And we usually write them alphabetical, so we could say AB. So I got force AB, and I have force then AC, don't I? So I will say AC, and this is 45 degrees. Now you might have wondered, well, why did you draw AB going this way and AC going that way? Well, I am assuming that this is in compression, and I'm likewise assuming that this is in tension. And a lot of times with trusses, on the top chord, when you start to look at a truss, there's some terminology here. You talk about the top chord, that's those pieces. The bottom chord, that's those pieces, and these pieces in between, these are called the webs. Okay. For a lot of trusses, when they're loaded in their use, when they've got forces going like this, the top chords are in compression, the bottom chords are in tension, the webs are a little harder to figure out. Now that's not always true. If we were to have a hurricane and have this in a roof structure and the roof's now trying to blow off, those loads are going to reverse. But oftentimes your top chord will be in compression, your bottom chord will be in tension. Now it's not a big deal if you miss this. You're just going to have a negative sign is going to correct you. If we get a negative, if we've assumed that this is compression and we get a negative, we'll know that our assumption was wrong and indeed it's in tension. So we have two unknowns here. We have two equations. We should be able to solve it. If we had three equations, that would just mean that we'd have to go do a free body diagram somewhere else, glean some information, and come back. Okay, and we'll have some of those problems in the future that will challenge us. So let's try this. Sum of the forces in the vertical direction, setting that equal to 0, what do I have? I have 500 minus, does this have a vertical piece? Yes, minus AB times the sine of 45, 2 over 2 if you rather. So we could say then that AB is equal to 500 divided by sine 45. Okay, and I've got a number here that should be, what, 707? Double check that. Yeah, 707 pounds. Now I got a positive on this, so what can I say about AB? I could say that AB is equal to 707 pounds in, it's positive, so it is compression. Okay, and that is a proper answer. We have proper significant figures, we have the units, and most important, we've called tension or compression. Because a lot of times, the most important thing is tension or compression. Whether this is 200 pounds or 1,000 pounds doesn't really matter to me a lot of the time. Because if I put a 2x4 in there, it'll probably hold both of those just fine. But if it's in compression, it better be something that can handle buckling. I certainly would not want to put a cable in here if it's in compression. So a lot of times, this number is not the most important part, but rather whether it's in tension or compression is the huge part. Well, let's finish this portion up. Sum of the forces in the horizontal direction is equal to 0, which gives me that's 0. So I'll just have AC minus now the horizontal component of that, which is AB times the cosine of 45, or 2 over 2. When you put that into there, you get that AC is equal to 707 times the cosine of 45, which had better get me back to 500 pounds, right? Yeah, 500 pounds. Just double checking my math there. So what I could say here is that AB, no, not AB, AC is equal to 500 pounds. This was a positive number indicating this was true, so it is in tension, isn't it? 500 pounds in tension. Okay, 500 pounds in tension. So if I go back and I look at the given, I've got AB, I've got AC, I need to come over and find BC, don't I? And I could do that with a free body diagram either at C or one at B. Why don't I move up to B? So if I look then at a free body diagram at B, what's that going to look like? Well, I have AB. I'm going to draw that in compression because I know it's 707 pounds in compression. I have then this, that's BC, and I have this acting straight down, this 1,000 pounds. Some geometry here. Let's see, this would be 45, this would be 45, so that would be a right angle, wouldn't it? So I could say if I sum the forces in the vertical direction, setting that equal to 0, that I have 707 times the sine of 45, or 2 over 2, plus BC times the sine of 45, that's a vertical piece there, minus 1,000. That whole thing is equal to 0. That's my equation right there. So I should be able to solve for BC is going to be equal to 1,000 minus 707 sine 45, and then I have to divide both sides by sine 45. I think that's probably going to turn out to be 707, isn't it? Yep, So 707 pounds. So what can I say about BC? That BC is equal to, this is a positive number indicating that my compression, this is in compression, so I can say it's 707 pounds in compression. Okay. Now, some of you might have said, well, I could have done that because I know this is 707 in compression. I could have gone over here and got that. That's actually true. If the problem is geometrically similar, that is, the geometry is the same, you could mirror it, and the loading is the same, that we didn't, you know, if someone had come in and they'd put a horizontal load like that, then this would not be true. But if the loading is symmetrical and the geometry is symmetrical, we see the members loading as being symmetrical. Now, could you go on and do a free body diagram at C, or even finish at B for that matter? Page 4, this is 5. So we asked some questions here. What if you would have taken this one and you would have at B said sum the forces in the, we did the vertical there, the horizontal, setting those equal to 0. What would you have to say? Well, you'd say 707 times the cosine of 45 minus BC times the cosine of 45 is equal to 0, right? Those are the only two pieces that are horizontal. So would we get BC that same way? We could say that BC times cosine 45 is equal to 707 times cosine 45. So that gives us a little more confidence in that answer, and that would have been the easier way to go. Now, what about a free body diagram at C? Back over here at C. Well, we know most of this, don't we? We know that this BC, this is BC, turned out to be what? 707. Isn't that what we got? Yep, 707 pounds in compression. And then what do we have? AC. Do we know that? I think we do. AC, 500 pounds in tension. 500 pounds in tension, and that has to equal then our reaction. What did we get for our reaction here? At C, we got 500 pounds, didn't we? So I can ask the question, is the vertical component of this equal to that? And is the horizontal component of this equal to that? And if you do, some of the forces in the vertical direction better be equal to 0. And some of the forces in the horizontal had better be equal to 0. So you could actually check it with that if you wanted to. I won't go through that, but you could, if you wanted to, check it with that. One thing that I would like to look at this problem before we leave it is, what happens if we were to design or build the problem a little differently? We started out with a problem that looked like this. And we had this 1,000 pounds here. And what happens if I would have put a member here, like this? Okay, so I would have added a member and another joint down there. So now I would say that J is equal to, we'll say this is what if. J is equal to what? 1, 2, let's see, 1, 2, 3, 4. That's the number of joints. And the members is equal to 1, 2, 3, 4, 5, right? 5 members. So I could say that 5 plus 3, is that equal to 2 times 4? Yeah. So we should be able to do this. This is okay. Now the thing I would like to do is maybe look at a free body diagram down here. What does that free body diagram look like? I have that pin, and I have this force there, and I've kind of put another pin in here, so my lettering's going to be messed up. So I'll just take this as the tension force here, and this one is the tension force there. And then if I look at this, you might say, well, you probably have a force there coming down in that, right? And these would be at right angles, although I don't necessarily need to. I've drawn them at right angles, though. So if I sum the forces in the vertical direction, setting that equal to 0, we'll say, we'll use this as our king post. That's sometimes what they're referred to as the king post. So we'll talk about that in terms of the king post. So I could say that I have the force in the king post. Anything else? Any other force? This is at right angles here. So I don't think I have anything else. So what do we recognize? We recognize that the force in the king post, that this force is 0. And we have what's known as a zero force member. That this loaded like this is a zero force member. Okay, and once you recognize that as a zero force member, then your analysis is really going to go back and you're going to analyze this thing just like we did this problem. So we'll talk in the future, get practice hopefully on looking for zero force members. It was a real tip-off that this is a zero force member because I had no load there. If you had a load there, then that would certainly not be a zero force member. But since I had no load there, it's a zero force member. So we'll talk about zero force members because it's kind of nice. If you can, by inspection, rule those out, you can get through the analysis a little faster. Although you've noticed here, even if you don't recognize it as a zero force member, if you're honest with your analysis, it will tell you that it is a zero force member. So sometimes you'll see those in trusses. Sometimes they're there for no reason at all, bad design. Sometimes they're there because the load might reverse. I mean, if you start to put if this is a roof truss and you put a ceiling load on it, this might have some load here, and it's not a zero force member. Or remember, if we get in a windstorm and the roof tries to blow off, our loading all of a sudden reverses, and we might have a different situation. So we'll see that. All of these vertical pieces are not necessarily zero force members, but in this application where I had no load down here, that was certainly a zero force member. So we've talked about a lot of things: introduction to truss design, introduction to method of joints, and also looking at some zero force members. So when we get together next time, we will continue on this. We'll do some more challenging problems with method of joints, and then look towards continuing on with method of sections. So thank you for watching, and take care till then.